Hi guys, welcome back here at DEC Engineering Tutorial. So this time is we're going to talk about design of drainage channel. Okay, so the hydraulic design of a drainage channel requires an excellent knowledge of the topography and rainfall data of the project area. So the design of the drainage channel is affected by the factors such as the topography of the project area, selection type, design frequency, expected volume of stormwater, and economy. The design discharge is affected by the channel section, the channel roughness, the channel slope, and the runoff coefficient factors. The primary consideration for the final selection of any drainage channel is that its design should be based on the appropriate hydrological, hydraulic, and geotechnical analysis, which will lead to economic and efficient hydraulic control system. So these are the types of channel. We have the natural channel. It is one with irregular section of varying shape developing in natural ways such as rivers, stream, etc. Artificial channel, it is the one built artificially for carrying water for various purposes such as canals. No? Open channel, a channel without any cover at the top such as canal, rivers, streams, etc. Covered channel, a channel having cover at the top, no? Such as partially filled conduits carrying water. And we have also prismatic channel, a channel with constant bed slope and cross section along its length. So constructed open channel frequently serve as a drainage ways in stormwater management system. A common feature of channels is that they are usually dry when there is no surface runoff and are designed to accommodate the peak runoff rate from a design storm. The drainage channel are commonly found alongside the roadways and therefore closely linked to the transportation infrastructure. So we have this one. Tsaka this one, no? Dito dry, this may tubig eh. So constructed open channels are designed in two types. We have unlined channel, so sometimes called as earthen channel or simply excavated channel in the ground through which water flows. These lining are again classified into two types and they are as follows. We have compacted earth lining and soil cement lining. On the other hand, line channels, excavated channels in which various lining materials are placed on the bottom and sides of the channel to provide stability and prevent erosion. It is subdivided into two types. We have rigid linings and flexible linings. So to illustrate that one, so provided this is the excavated part of the land, so we have this channel lining. So we have the top width, the depth of the water, and we have the bottom width of our channel. And we have this pre-board, no? So if we add embankment, so the pre-board also goes up to the top embankment level. For the unlined channel, so yung mawawala lang dito is itong channel lining. We have unlined channel. So if you see depth nung flow natin, it is the vertical distance of the lowest point of the channel section or the channel bed, no, from the free water surface. So if we say depth nung flow section, it is the depth of flow normal to the bed of the channel. We have the top width. It is the width of the channel section at the free surface. We have also weighted area. It is the cross-sectional area of the flow section of the channel, yung nabasa lang nung tubig. And we have also weighted perimeter, yung lining na nabasa lang din ng tubig. It is the length of the channel boundary in contact with the flowing water at any section. We have also hydraulic radius. No? It is the ratio of cross-sectional area of flow to the wet perimeter. Okay, so earth canal, the most common type of irrigation conveyance channel is the one excavated in natural material along the line that water must be conveyed. No? The low initial cost constitutes the major advantage of earth canals. The disadvantages are we have excessive seepage loss, low velocity, therefore relatively large cross-sectional area, danger of breaks due to erosion and burrowing of animals, favorable condition for growth of moss and aquatic weeds which retard the velocity and cause high annual maintenance costs. The sides of earth canals are usually built as steep as the earth will stand when wet. The relation with bed width B to the depth of water in the earth canal D is determined according to the topographic condition. The best hydraulic cross-section under favorable structural condition is B must be twice the depth multiplied by tangent of theta divided by 2, where yung theta is the angle between the side slope and the horizontal. This relation applies also to line canals. For rectangular channels, the bed width equals twice the depth for best hydraulic characteristic, or simply B equals twice the depth. Okay, so lining canals. Irrigation canals are lined for the purpose of decreasing the conveyance seepage losses, providing safety against breaks, preventing weed growth, retarding moss growth, decreasing erosion from high velocity, cutting down maintenance costs, reducing drainage problems, and also increasing the capacity to convey water. And these are the materials used for canal lining. We have concrete, rock masonry, brick, bentonite earth mixture, natural clay of low permeability, and we have also different rubber, plastic, and asphalt compounds. So concrete lining has a high initial cost, but several advantages. We have durable, minimum maintenance costs, and also increased capacity due to smooth surface. Earth materials are used for canal lining, especially when lower initial cost is necessary and when suitable materials are available. Three methods employed is placing a blanket of relatively impervious materials over or within the impermeable canal bed, dispersing clay in the water, having it filter out as the water seeps through the channel bed, or chemically stabilizing the earth material to make it less pervious. The most common material used for method of stabilizing water is to mix about 10% of the Portland cement with a moist soil and compact the mixture. Thorough mixing, often difficult to secure in practice, is essential for a satisfactory, relatively durable lining. Asphalt, plastic, and rubber compounds are becoming more widely used for linings in canals and ponds. So 10 layers are often covered with earth for protection. Thicker layers and build-up section are used when resistance to abrasion and mechanical damage, as well as durability is needed. Also considered maintenance when choosing a channel lining. So, kung sa design pa, parang serviceability. So, the channel will need to be accessible by mowers and trucks mowing. Side slope of vegetated channels will need to be traversable for mowing equipments and crew. Dapat. The maximum traversable slope for this equipment is 1:4. And if you consider the access across the channel, if there is a rubble riprap lining the channel and vegetated buffer on the backside of the channel along the right of way, the irregularity of the riprap typically prevents access. In this situation, it may become impractical to maintain the vegetation. Hand lever materials of canal lining are being replaced by bulldozer, dragline excavators, and tractor drone chains. So most common method of controlling weeds on the canal bank is pasturing, mowing, burning, and application of chemical weed killers. And we have also methods of controlling water weed growths may be classified as mechanical, drying, shading, and chemical. Aromatic solvents are most economically in small channels, while mechanical methods of weed control are more practical and more economical on larger canals. Okay, so let's go to open channel flow. An open channel is a conduit in which a liquid flows with a free surface. An open channel flow is the one in which the stream is not completely enclosed by solid boundaries and therefore has a free surface subjected only to atmospheric pressure. The flow in such channel is not caused by some external head but rather only by gravitational component along the slope of a channel. Thus, open channel flow is also referred to as a free surface flow or gravity flow. Example of open channels are rivers, stream, canal, and etc. So, ito no. So we have this closed conduit and we have this open conduit, no. But they are subject to atmospheric pressure, no. So comparison between the open channel flow and pipe flow, no. So we have these different aspects, no. In terms of cause of flow, for the open channel, it is caused by gravity, while in pipe flow is caused under hydraulic pressure. In the aspect of cross-sectional shape, open channel may have variety of shape, no? It could be triangular, rectangular, trapezoidal, parabolic, or circular, while pipes are generally round in cross-section, and that is uniform along its length. In the aspect of surface roughness, so for the open channel, it varies with the depth ng flow natin, while sa pipe flow, it varies on the type ng material na ginamit sa pipe. In terms of piezometric head, we have this Z plus H, no? Where H is just the depth ng channel. While yung sa pipe flow, that is Z plus this pressure head, no? P over this density of water, where yung P is yung pressure ng pipe. And in the aspect of velocity distribution, yung maximum velocity occurs at a little distance below the water surface. The shape of the velocity profile is dependent on the channel roughness, while in the pipe flow is symmetrical about the pipe axis. So maximum velocity occurs at the pipe center, and velocity at the pipe walls reduced to 0. So sometimes for laminar flow, we can get a parang parabolic, no, na shape ng velocity versus height diagram. Okay, so these are the types of flow in open channels. So it may be classified in several ways. We have steady and unsteady flow, laminar and turbulent flow, uniform and non-uniform flow, and we have also subcritical, critical, and supercritical flow. So the meanings of the term steady state and unsteady state are the same for open channel flow as for a variety of other flowing fluid application. For steady state flow, there are no changes in the velocity pattern and magnitude with time at a given channel cross-section. Steady state open channel flow takes place when there is a constant flow rate nung yung discharge na, yung Q of the liquid passing through the channel. Ngayon kung nagbabago yan, and that is we call it unsteady state flow. Okay, so unsteady state flow, on the other hand, does have a changing velocity with a time at a given cross-section. So unsteady state open channel flow takes place when there is a changing discharge or flow rate, as for example in the river after a rainstorm. So for laminar and turbulent flow, classification of a given flow it can be either laminar or turbulent. This is important in several fluid flow applications such as pipe flow and flow pass, a flat plate, as well as in open channel. In each case, a Reynolds number is the criterion used to predict whether a given flow will be laminar or turbulent. So usually, commonly, no, sa open channel, turbulent siya, no? Turbulent. Mannings is derived under the consideration na turbulent flow siya. Okay, so for open channel, it is defined with the Reynolds number. We have this formula. And for pipe flow, we have this formula. So, if yung Reynolds number natin is less than or equal to 500, we consider it laminar. And if it is in between 500 and 1000, we call it transitional flow. And if it is greater than or equal to 1000, we call it turbulent flow. So, remember in pipe flows also, if it is less than or equal to 2000, we call it laminar. Else, we call it turbulent. So, we can use Modi chart, no, actually, for pipe flows. Laminar flow is also sometimes called streamline flow. So it occurs for flow with high viscosity fluid and or low velocity and or high viscosity. Turbulent flow, on the other hand, occurs for fluid flows with low viscosity or high velocity. So we have also supercritical, subcritical, and critical flow. So any open channel will be supercritical, subcritical, or critical flow. The difference among these three classifications of open channel flow, however, are not as obvious or intuitive as with the other classification, such as steady or unsteady, laminar or turbulent, uniform or non-uniform. Your intuition will probably not lead you to expect some of the behaviors for subcritical and critical flow and the transition between them. Subcritical flow occurs when the relatively low liquid velocity and relatively depth flow, while supercritical flow occurs when relatively high liquid velocity and relatively shallow flow. So, masabtan naman siya, no? So, yung ginagamit natin as criterion is yung Froude number, which is equal doon sa velocity over the square root of the gravity multiplied by length. So, can be used to determine whether a given flow is supercritical, subcritical, or critical. So, if yung FR natin is less than 1, then it's subcritical, no? If it is greater than or equal 1, then it is supercritical. I mean, greater than 1, that is supercritical. If equal to 1, that is critical. So, napaka-importante nito in the design of channel section. Okay, so, bali ito na yun, no? Yung Froude number is just the ratio of inertial force due to ratio of inertial force to gravitational force of flowing water. Mathematically, it is velocity over square root of 2gh. So, yung h or yung L, yan yung depth nung flow natin. Yung G is the gravitational acceleration, while yung V is the average velocity nung flow. So, ito na yun, no? Kung less than, subcritical, equal, critical, pag greater than, supercritical. So, to illustrate that one, we have, let's say, yung x-axis natin stands for energy. And yung y-axis natin stands for the depth nung flow natin, no? So, we have this potential energy, no? Which is linear, no? And we have this kinetic energy, no? We have velocity squared over 2 times the gravity. So, if we sum this up, this potential energy and kinetic energy, we called it specific energy, no? We have this potential energy y plus the kinetic energy, which is the velocity head. So, at this position, we call it the critical depth, where also corresponds to the minimum energy. Okay? So, critical depth occurs at minimum energy. So, above the critical depth, we have this subcritical flow. When the depth of water is equal to the critical depth, then we have the critical flow. This critical flow, or this YC, is constant. No, is constant for our channel bed. Anyway, makikita nyo yan mamaya. And we have also, pag below YC, that is supercritical. So, if we graph the discharge versus the depth of flow, so we have this chart, no? So, yung YC or yung critical flow also corresponds to the maximum discharge, no? So, bali sa YC, meron kang minimum energy. At the same time, you have the maximum flow rate. So, again, that is subcritical flow, supercritical, and critical. So, yan, no? So, ito na yung depth ng water. So, we call it critical stage. So, pag below that, yung depth ng water natin, we call it lower stage. And pag above that, we call it upper stage. So, ito yung tinatawag natin na supercritical depth. No? From the datum to, from the bed ng slope natin to the lower stage water surface. Then, we have also critical depth and subcritical depth. And we have this velocity head. Okay, so dito sa water surface, we call it HGL or hydraulic gradient line. And dito naman hanggang kinetic energy or velocity head, we call it EGL, no, or energy gradient line. So in summary, so we have these different aspects in terms of depth of flow, velocity of flow, slope ng uniform, fluid number, velocity head. So we have this different comparison based on different aspects. Like nakasummarize na siya dito. Okay? So madali siyang tandaan din. So critical depth. The general equation for determining the critical depth is ito, no? We have Q squared over we have this discharge squared over the acceleration due to gravity is equal doon sa cross-sectional area cube over the top width nung water surface natin. And we have this critical velocity, which is again defined as square root of the gravity due to acceleration multiplied by the cross-sectional area over the top width of the water surface. Okay, so another category ng channel flow is we have this one, no? Uniform and non-uniform flow. Okay, so uniform flow will be present in a portion of the open channel called the channel reach with a constant flow rate of liquid passing through it, constant bottom slope, and constant cross-sectional shape and size, like constant lahat, no? All throughout from different cross-sections. So with this condition present, the average velocity of the flowing liquid and the depth of flow will remain constant in that channel reach. So for instance, so bali yung slope nila is the same, no? And so we have this different section 1, 2, and 3. So like uniform yung cross-sectional nila lahat. So we have this normal depth and we have this energy gradient line, no? Ayan. So yan yung mag-flow ng water. That is E, uniform flow. So for each case of channel where the bottom slope, cross-sectional section, and cross-sectional size change, non-uniform flow will occur. So whenever the bottom slope and channel cross-section shape and size become constant in the downstream reach, another set of uniform flow condition will occur. So meaning in a channel design, we can have a combination of uniform and non-uniform flow. So for instance, no, ito yung example ng non-uniform, no? From the mild slope to steep slope. So we have this S1 and S2 and they are not equal. So yung mangyayari, we have this critical depth which is constant all throughout yung channel natin. And we have this YN, no? And we have this another YN at the steep slope. So yan, no? So meron tayo ditong a drawdown curve. So bali yung flow ng tubig natin is pag ganito, no? So meaning, itong drawdown na to, we call it gradually varied flow or GVF. So meron din tayo yung GVF dito. Okay? So ito yung GVF considering the mild slope. Ito naman yung GVF considering the steep slope. So bali yung flow ng tubig is pag ganito. So pag ganyan, ha? So bali dito, sa section 1 up to this point, we have this uniform flow, no? Pero dito sa GBF na part, that is non-uniform flow. Then after that, we have also again uniform flow. So makikita mo na meron siyang combination ng uniform and non-uniform flow. So we call it drawdown curve. On the other hand, we have this steep slope to a mild slope. So ganun pa rin yung mangyayari, no? We have this different channel bed slope. And we have this critical depth, no? All throughout ng section natin. That's fixed. So we have this YN. And we have this YN at the mild slope, no? So bali itong YN na to, this is supercritical. And we have this subcritical, no? Kasi mas mataas pa siya sa critical depth. So pag mas mataas sa critical depth, that is subcritical. Pag below nung critical depth, meaning that is subcritical, meaning malakas yung velocity dito compare dito. Okay, so bali yung mangyayari dito is yan, no? So meron tayo ditong hydraulic jump na mangyayari. Ito yung hydraulic jump curve. Okay? So that would be the first possibility. The second possibility of hydraulic jump would be, of course, at the mild slope, no? Pwede din, no? That could be the second possibility. So dito sa hydraulic jump, we call it rapidly varied flow or RVF. Then after that, meron na tayong GVF pagkatapos, no? And then ganun din dito, no? We have this GVF and then mag-hydraulic jump siya, no? Which is RVF. So bali yung combination ng RVF tsaka GVF, non-uniform yan. Non-uniform flow, no? So these are, we call it hydraulic jump. So yan. So yung first possibility, yung mangyayari is ganito yung flow ng tubig. Sa second possibility, yung mangyayari is ganito yung flow ng tubig. So makikita mo, meron siyang non-uniform flow. So yung issue natin dito is enough ba yung depth, no? Yung depth ng channel natin. Di ba? Yan yung concern mo sa design. Okay, so in the next video, I'm going to present the derivation of CHEZY formula and other steps related to the design of drainage channel. Okay, so yeah, keep on watching. Thank you.